Hello, my name is Ralph Dawes. I teach geology for Wenatchee Valley College in central Washington state. I'm here to give a talk titled Reading the Okanogan Lobe Glacial Landscape. And with that, let's go to the slideshow that I will talk over. Bring it up to size. Here we go. And bring up a pointer. So there's that title, Reading the Okanogan Lobe Glacial Landscape. My name and my email contact if you have any comments, questions, or perhaps corrections. In the background from this Google Maps rotated image, you're looking at the southern part of the Okanogan Lobe glacial landscape, but we'll get to other maps and images as we go. So here's an outline of what I'm going to talk about today. First of all, why study this landscape, this Okanogan Lobe glacial landscape? Second, what is the Okanogan Lobe? It was part of the Cordilleran Ice Sheet. Well, what is that? What, where, and when were those things? The Cordilleran Ice Sheet and the Okanogan Lobe. Then we're going to get into, for most of the talk, the landforms, these shapes created or left on the landscape by the glaciation. So these glacial landforms, and I'm going to group them into four categories for consideration. Elongate ridges that formed beneath the ice sheet or glacier, certain types of valleys that form under glaciers and not outside the glacier. Well, maybe they do form outside the glacier in some cases. We'll have to look into that. But unusual valleys associated with the glaciation. Terraces, flat-topped terraces in the landscape along the sides of valleys. Those were left after the glaciation. We're going to consider how those formed. And these things called hill-hole pairs. Should be pointing to these things as I go, I suppose. How did these landforms originate? That's the question I'm delving into, along with looking at the characteristics and examples of each as we go. Okay, so that's the overall outline of what I'm going to cover. But click here, advance. Let's start with why study the Okanogan Lobe landscape. First of all, to determine in geological terms how the landscape formed. You know, in Earth history terms, in terms of how the Earth works and how ice sheets work. How did that create this landscape? That's still being debated and still a matter of ongoing research by other geologists. So that's worthwhile right there. It's a set of unanswered questions in some ways, geologically speaking, scientifically speaking, to look into. So there's that pure knowledge aspect. This landscape is just north of a different landscape, almost overlapping landscape called the Channeled Scablands, which are in eastern Washington and parts of Idaho and Oregon adjacent to that. And the Channeled Scablands, you may have heard of them. That is a landscape that was formed by gigantic floods during the ice ages, floods caused by the glaciation to the north, which went tearing across the Columbia River drainage system and tore basalt off this, down into these scablands and eroded these coulees or steep walled, deep canyons into the basalt layers that fill in eastern Washington. Anyway, that's the Channeled Scablands. How is that related to the Okanogan Lobe in particular? I won't have the answers to that completely, but it's something that comes up in terms of why study the Okanogan Lobe landscape. Because if we need to understand how the Okanogan Lobe landscape originated and how the Okanogan Lobe glacial system operated, if we're going to finish understanding the connections with the Channeled Scabland to the south. Studying a place where an ice sheet used to be and how it advanced and how it operated and how it melted away and retreated at the end gives us insight into how these things work when the climate gets colder or the climate gets warmer, including what's happening and is going to happen under the Greenland Ice Sheet today, which is of a similar size and sitting on a somewhat similar landscape to what the Cordilleran Ice Sheet sat on back when the Cordilleran Ice Sheet existed. And we don't completely understand, we're learning as it goes how the Greenland Ice Sheet is melting and is going to melt. So we can gain some insight into how that's going to happen in the future, the more we figure out the Okanogan Lobe glacial landscape. The plants, animals, and people in this area are all strongly affected by and living in the presence of this glaciated landscape. And so once we know this landscape's geology better, we can predict better such things as where the aquifers are and how big they are. In other words, the water you can get out of the ground if you drill a well into it, what the soil types are, which derive from what the geology was underneath before the soil formed, which is, we need to know that for the agricultural planning and so on. Landslide hazards relate to what the ground is made of, which we'll understand better when we know the origins and characteristics of this landscape. And such things as sand and gravel resources. This picture at the bottom right shows a gravel quarry in Okanogan, Washington, and they are quarrying sediment left by the Okanogan Lobe of the Cordilleran Ice Sheet. Okay, I'm going to add a couple more things for why I study the Okanogan Lobe landscape. These are my personal motivations. One is that my wife and I moved to Omak, Washington, in the middle of this landscape in late 1998, and I started teaching for the Omak campus of Wenatchee Valley College in 1999, and I was teaching geology, so I had to learn the geology of the area to take students on field trips and to know my place-based geology. So I got into the basic stories, the published papers, the mainstream story of what was accepted for as much as I could figure it out at that point. And so, I got into it. It's a wonderful, unique place, this glaciated landscape of the Okanogan Highlands and the Okanogan Valley and adjacent areas. It's special because of these glacial features. And anyone who's lived there or visited there and paid attention to the landscape, you know this. It's a unique place in terms of its landscape. But then I transferred. We moved down to Wenatchee, so I taught geology at the main campus, about 100 miles away in the center of Washington State, beyond where the ice sheet and the Okanogan Lobe ever reached. But I still visited up to Omak and the Okanogan Lobe. And in the 2010s, about 10 years ago, I went to a talk in Wenatchee by a proponent of an alternative explanation for how many of these major landforms could have been created under the ice sheet. And this was the meltwater underburst hypothesis from Shaw and others, 1999, and I'm going to talk about this a little bit more, so I'll give you more details. And Lessman and Brennan in 2009 published a follow-through paper looking at more detail into this hypothesis for the Okanogan Lobe region in particular. So instead of the ice causing most of the land forming, this was giant floods of water under the ice sheet. That's the alternative. That's the meltwater hypothesis. That was quite eye-opening and in some ways compelling. You could explain so much at once with one giant flood or maybe a few giant floods, and that would connect right down to the Channeled Scablands and explain much of the flooding down there as well. So I had to, gear up and reconsider and look at these things again in more detail. That was my second round of motivation to look into this landscape and how it formed. Okay, that's my personal motivations. My methods are first of all, I'm not doing that much original research in great detail. I wish I had more time. I am doing some ground truthing and checking out the evidence on the ground for the competing hypotheses and for the characteristics of these landscapes. But I am basing a lot of this on what I've read, the published geological literature and the published geologic maps, and also the maps data you can now get through the internet, which previous generations or even just a decade or two didn't have all that data available to analyze landscapes, through the computer based on what satellites and other means have put together. And then visit the field area and look at these things in detail. That's important because this has to be evidence-based. This is the scientific approach, of course, and then it has to make sense logically. You can apply math to it. It has to make sense in terms of the so-called laws of physics. And then overall, I'm looking for my read on this landscape is the one that I think fits best all the aggregated evidence, not just one piece of evidence in one place at a time, but also how it all fits together into a larger picture. So those are my methods. So what was the Cordilleran Ice Sheet? It's also pronounced, and it's perfectly acceptable, I guess, the Cordilleran Ice Sheet. You'll hear it either way. That was a giant glacier, but so what's a glacier? A glacier is a flowing body of ice. It's a body of ice that forms from snowfall that accumulates on land in a climate that's cold enough that the snow doesn't melt in the summer. So year by year, you get more and more layers of snow that have built up and have not melted away, and they push the more recent snowfall layers, annual layers, push the older layers down, compact them, get rid of the air bubbles, turn it into ice, and eventually there's enough thickness and mass that it starts flowing under its own weight. Okay, and then it's a glacier. It doesn't just sit there. And there's two broad categories of glaciers: the alpine glaciers and the ice sheets. Without much overlap in between, they're pretty distinct. Um, an ice sheet is far larger than an alpine glacier. An ice sheet covers, if not a whole continent, a significant portion of a continent. And so they're also called continental glaciers. The ice sheets are. There's currently the Greenland Ice Sheet and a couple ice sheets covering Antarctica in the world today. Back during the last coldest part of the last ice age, not that long ago, there were other ice sheets, including in North America. And an ice sheet is big enough; it doesn't just form in the mountains and fill the valleys in the mountains like alpine glaciers do at their largest. An ice sheet can flow right over a mountain range. Okay, so that's big. Here's a couple cartoonish illustrations. Alpine glaciers on the left of several types. And then, so you have valley glacier, cirque glacier in an amphitheater-shaped valley up in the mountains. This valley glacier actually is coming out and spreading onto the lowlands at the base of the mountains as a Piedmont glacier. You can see where my pointer's pointing. This is just a valley glacier that doesn't come out beyond the mountains. There are still cirque glaciers and valley glaciers in the North Cascades or in the Cascades Mountains today, alpine glaciers there. Here's a continental ice sheet, vertically exaggerated, supposedly covering a portion of a continent and partly going out along a coast into the edge of the ocean. And that's, there could be mountain ranges under this ice sheet. That's how big it is. Well, here is a map I took from a website, I think Idaho State Geologic Survey or Idaho State University. Anyway, the details are on there. The Cordilleran Ice Sheet, so the ice sheets are in blue on this map of the northern 2/3 of North America, including Alaska at the top left, the 48 state region of the United States today in the bottom, and then Canada makes up most of the middle of this image. Well, there's a bigger ice sheet covering most of Canada and parts of the north central and northeastern United States at last glacial maximum, the last time these ice sheets got to their largest, which was roughly 20,000 years ago, but it depends on where you look for where they reach their maximum. So I gave it a very broad, stretched out 25,000 to 13,000 years ago, last glacial maximum interval. This is a little bit of an out-of-date map. So the Cordilleran Ice Sheet is on the west or left, and it's smaller than the Laurentide Ice Sheet, but it's still huge, covering southern Alaska, British Columbia, parts of Alberta, and parts of other adjacent provinces in northwestern Canada, and parts of, okay, see my pointer here. This would be the Puget Lobe or Vashon Lobe down in the Puget Sound region of western Washington. About here, this is supposed to be the Okanogan Lobe, a lobe-shaped part of it sticking out in the south central part of the Cordilleran Ice Sheet into the north central Washington state, etc. But this pink area, according to this map, was not glaciated at last glacial maximum by these ice sheets, but actually it was. So this, like I said, this map's a little bit out of date. At last glacial maximum, you got to push these two blue ice sheets completely together and close this corridor off. Okay, so this is evidence based, but it's also based on reading and looking at maps that other people have published. So here is from Canadian geologists, the references on the bottom left there, from a compilation map that they put together, interpreting which way the Cordilleran Ice Sheet was flowing across the landscape based on landforms interpreted as indicating ice flow direction on the ground. And this compilation map has thousands of these data points. So the arrows or just the linear features show which direction the ice was flowing across the ground the last time it left these landforms. And there's a variety of landforms. I'll get into some of them in a minute. So that's just one type of evidence, flow directions from landforms, flow directions that the ice was apparently flowing last time it left its mark on the surface of the Earth. You can look for there's lots of other types of evidence to look for, such as the there are mountains in the Cordilleran Ice Sheet region that get up really high, in some cases over 10,000 feet, and a lot of them over 7 or 8,000 feet. And some of them protruded out of the top of the ice sheet even when the ice sheet was at its thickest. So those are called nunataks, as in this illustration at the bottom left, this photograph from Greenland showing some peaks sticking up out of the ice. Those are nunataks. Well, there are apparently nunataks, like in the Coast Range of British Columbia and in the Rocky Mountains in some cases, because it covered both those mountain ranges. And if we're confident we can see how high up on the side of those mountains the glacier got, then that gives us a marker for how high above sea level the top of the ice sheet was at that location. And another example of evidence, and there's lots of other examples, these are just examples, is moraines. Moraines are landforms made of sediment left by the glacial ice, mixture of boulders on down to clay size of all these types of sediment put together in one deposit by the ice itself. And then the glacier is gone and the moraine is left behind, made of this material called glacial till. And at the farthest reach of where the glacier got to, it piles up the moraine of this glacial till around its margin, known as it's called a terminal moraine, but that marks how far out on the landscape the glacier got, along with looking for the other signs of where the glacier flowed to verify that it was within the what we're thinking is that terminal moraine zone. So we have a pretty clear picture of where it was, how it was flowing, the last time it was flowing at any rate, how far it got to the Cordilleran Ice Sheet, and that particular somewhat small part of it called the Okanogan Lobe. Here's another picture on a simplified map. And let's see. So what I want to show you on this one, this simplified map from Clegg 2009. So most of this white area is the Cordilleran Ice Sheet. This shows a little bit of the Laurentide Ice Sheet, the giant ice sheet that covered a larger area of the rest of Canada and so on. And they met up along here. And again, at last glacial maximum, there shouldn't be any gray in here. It would be all ice at the very, during at least a few centuries or up to a couple thousand years when the ice was totally at its maximum. So that corridor was blocked off and the two ice sheets met up with each other. But what I want to focus on here is these big, bold black lines. Those are the ice divides. So based on which way the ice was flowing on the ground, there are places where it flowed in opposite directions on either side of where they've drawn these lines. That means the surface of the ice sheet was like a ridge up there. I mean, not a steep ridge, but it's a divide between flow directions coming out, because the ice flows downhill from higher to lower along the surface of the ice sheet. Okay, that slope of the surface of the ice sheet determines the primary direction that the ice is going to flow. So the ice flowing south here must have been separated by a so-called ice divide from the ice flowing north here. Okay, so what I'm calling the Okanogan Lobe it consisted of ice coming generally south from this ice divide in south central British Columbia, crossing over a latitude of about 50 degrees north above the interior plateau of British Columbia, rather than some high mountain source. Okay, but the ice was so thick it built up here to send out flow in these two directions all the way down into the end of the Okanogan Lobe here in north central Washington State. If you can see my pointer on the bottom right. Another picture from another paper illustrating what I'm talking about here of the southern part of the Cordilleran Ice Sheet, again at last glacial maximum. This one, you can see the Puget Lobe or Vashon Lobe in western Washington. Here's Vancouver Island, Canadian border. So from the ice divide I've sketched in here between the opposite ice flow directions on either side of it, again around 52 degrees north in south central British Columbia. Anyway, the ice is flowing generally overall south. And here's the southern end, the terminus, the farthest point that the Okanogan Lobe reached. And along the edge of that is the pile up of glacial till or other glacially transported material known as the Withrow Moraine in north central Washington. And I refer to this whole corridor from the ice divide to the Withrow Moraine as the Okanogan Lobe. I mean, that's the whole landscape I'm talking about, even though just the southern part of it here is the part that technically qualifies as a lobe. Okay, now there's a interesting physics-based model, put in the equations, the laws of physics derived, how should I say this? equations from physics, which we know work well and are generally true, and then put them into a climate model where this is what Sagano and others did and published a paper in 2020. Put in a climate model for the temperatures that the ocean and the air were reaching in this area during the last couple 100,000 years or so. I think they ran this model back, and that includes two cold intervals when ice sheets could have formed, and then based on the laws of physics, does this model produce ice sheets, and if so, what does that tell us possibly about the Cordilleran Ice Sheet? So this is a theoretical reconstruction based on the laws of physics and the climate data through the last couple rounds of the ice ages, the Pleistocene epoch. I'll talk about the timing in a minute. Um, for the Cordilleran Ice Sheet, the blue color is the colors relate to how fast the ice is flowing, whereas dark blue, it's just about at a standstill, low speed. More dark red it turns, the faster the ice is moving. Okay. The black lines are contour lines for elevation above sea level in meters. So every bold black contour line is another 1,000 meters up from sea level. So the high parts of the ice sheet up here, which coincide with where the blue is for where the ice is moving slowly, are up to over 3,000 meters above sea level, up to over 11,000 feet above sea level, according to this model. That's really thick and high. Okay. And back to those speeds, the hotter colors equals the faster speed. So here's this model also produces an ice divide in south central British Columbia, and it produces a stream of relatively fast flowing ice coming down its version of the Okanogan Lobe that shows up in the theoretical reconstruction right here. And so that a fast flow zone like that, if it's a lot faster than the ice on either side, concentrated down one corridor or stream, that's called an ice stream. So there may have been an ice stream flowing right down the Okanogan Valley, and this theoretical model agrees with that. So the ice flow direction and speed are determined by the slope of the glacier surface, as I've already mentioned. The steeper it is, the more push there is to get the ice to flow. And then it also depends on what's happening at the bottom of the glacier, the bottom of the ice sheet. If it's frozen, if it's a cold base glacier, that means it's frozen to the ground. It's below freezing down there, and there's no liquid water. And that makes it very difficult for the ice to move or slide along the base across the face of the earth. So a cold base glacier hardly moves, if it moves at all, at its base, and the glacier flows by deforming plastically within the ice, and you have to get up above the ground, away from that friction, to get where the ice is moving faster. But it's still only moving so fast because deforming plastically flowing ice, it can flow surprisingly fast, but not as fast as, say, water or something like that. It's a solid material deforming itself or being deformed by the forces. But if it's a warm base glacier that has water at its base because it gets above freezing, and by the way, one way it can get above freezing, if there's enough pressure from the total weight of the glacier above, the increased pressure can drive it in some up above freezing and make it a warm base glacier with water at the base, etc. There's several factors in whether it's frozen at the base or has water to some extent at the base of the glacier. But if it does have water, then if it's wet at the base, then that's a lubricant, and it can slide and move a lot faster. So that's known from both theoretical and observation and evidence from previous landscape studies that if the glacier has water at the base, it's going to move at the base a lot faster. Overall, the ice is going to move a lot faster, and that's going to have a lot more effect on shaping the Earth's surface underneath, okay, where it's wet based and the ice is moving faster. Also affecting which way the glacier flows is the topography or shape of the land underneath. If there's a valley parallel to the flow, it can concentrate ice in there and speed the flow up, perhaps. Or it can block flow if there's a cross mountain range or ridge that's big enough, not block it completely, but impede it. And these same factors that control which way and how fast the ice is going determine how the glacier erodes and shapes the land underneath. Okay. Glaciers leave behind sediment, and those are key pieces of evidence, those bodies of sediment and types of sediment that the glaciers leave behind overall. So here's a few categories of sediment. There's glacial till, which is an unbedded, doesn't have layers in it in most cases, in most places. Unsorted mix. Unsorted means the big grains are mixed in with the small grains. They're not separated out into one grain size. And here you can see boulders, and it goes all the way down to clay size where it's dark gray. So it's an unsorted, unbedded mix. That's glacial till, left directly from the glacial ice. That's how it gets deposited. Then there's outwash, which is beds of sand and gravel, and sometimes it'll have boulders in it too, but they're at least to some extent sorted into different grain sizes by the flowing water and laid out in beds, deposited in beds or layers by the flowing water. So in contrast with the till, the outwash is deposited by meltwater coming off the glacier. Okay, then there's lake bed sediments, especially in a highly mountainous, deep valleys, high mountains landscape like the Cordilleran Ice Sheet in the Okanogan Lobe. There are going to be times and places where the ice, at least temporarily, dams valleys, dams stream drainages, and you get temporary lakes caused by the glaciation. And in those lakes, the water doesn't move fast, and fine grained sediments settle out into thin beds of very fine grained sediment, lake bed sediment, another common type of sediment left behind, telling you something about what the glacier was doing to the landscape in that area at the time those sediments accumulated. Okay. Timing. This talk is too long already, but speaking of timing, so I'm going to give it one slide. The Pleistocene epoch was about 2.6 million to about 12,000 years ago. It was during that time that multiple times the climate got cold enough, the global climate around the world, to form continental ice sheets in places like North America and Northern Europe, colder than the world is now by quite a bit. So that you have ice sheets far, that go well beyond Greenland and Antarctica like we have today. So these cold glacial intervals happened repeatedly between 2.6 million and 12,000 years ago, numerous times. The Okanogan Lobe, south of the Canadian border, the age measurements that have been done on what it left behind, such as organic material that you may be able to do a radiocarbon age measurement on, or boulders left exposed. Oh, I didn't mention in that slide about sediments and glaciers. It also had a picture of glacially erratic boulders. Glaciers move boulders around and they just leave them there in the landscape. And the boulders came from somewhere else up where the glacier was flowing from. Those are called glacially erratics. You find some good, nicely exposed glacially erratics. There, with some effort, you can measure how long that has been exposed to the atmosphere and to outer space, cosmic rays coming in and so on. You get an exposure age. And there's some other methods as well. None of them are perfect. Some of them have some ways that the measurement can go wrong, but by the material having been disturbed in ways that don't match the assumptions that have to be made to make the age measurement. But nonetheless, some of these ages are good enough to narrow down that the Okanogan Lobe, the age measurements we have on it existing and coming down and existing south of the Canadian border are between perhaps less than 20,000 years ago, and then it was gone by about 13,000 years ago from south of the border with Canada. Okay. And there may be a somewhat more restricted range than that because there's something like 1,000 years plus or minus on these numbers that I've summarized from the literature. South of the Columbia River, where it becomes the true lobe shape that you see on that map, down into the Waterville Plateau of northern Douglas County in north central Washington State. The Okanogan Lobe was, again, we only get these last round of glaciation ages on the Okanogan Lobe coming south of the Columbia River to reach its maximum extent, and that's between about 18,000 and 14,000 years ago. Again, plus or minus something like 1,000 years on those numbers. And maybe we'll have more improved, more precise, more accurate dates in the future to not have that much uncertainty about exactly when this happened. But those are pretty good limits on when these things happen. But it's different up in Canada, where they have found layers of sediment and evidence of earlier glaciations on the landscape. Just north of the border into the Lake Okanagan area in southern British Columbia are these features from this paper that is referred to here. So this is glacial outwash in their interpretation, and it's pretty strong evidence.
under what appears to be clearly glacial till. A diamicton means an unmixed, unsorted, an unbedded, unsorted mixture of sediment from big to small. But in this case, they've concluded it's a glacial till, this diamicton. So here we have evidence of glacier filling the Okanogan Valley, presumably an earlier version of the Cordilleran Ice Sheet, at a time before these basalt flows came out and erupted and solidified across this landscape. Okay. And these basalt flows are around 1 million years old. So taking that number, 1 million years, this glaciation was over 1 million years ago, or at least about 1 million years ago. That's pretty old. And they found a few other deposits of sediment up in Canada for a few other older glaciations besides the most recent one. So that most recent one was between up in Canada, roughly 30,000 and 12 or even 10,000 years ago by the time the last of it melted away. But there were earlier glaciations. And so it's important to keep in mind that the most recent ice sheet, including the Okanogan Lobe, part of it, covered most evidence of previous glaciations, eroded away most evidence of previous glaciations. But nonetheless, even though we aren't quite able to prove it yet, the Okanogan Lobe may have come down about as far as it did most recently in previous glaciations. And these glacial landforms, in many cases, could have been formed over the course of several glaciations, not just once. That complicates things, but that's the way it was. All right. So I want to focus on a question that comes up in debates about how these glacial features formed, which is the thickness of the ice sheet over the Okanogan Valley and the thickness of the ice sheet in general. I showed you that theoretical model where it gets up over 11,000 feet. That's not that far off from what the field evidence suggests, including how high it got up on the sides of the highest mountains, how high up the ice got for that on the top of that ice sheet across the surface. But if you go back over 100 years, early geologists didn't even think of it as an ice sheet. They thought all these glacial features up here in the Okanogan region and down into north central Washington were from alpine glaciers coming down their valleys and in some cases becoming Piedmont glaciers. Okay. And even so that was over 100 years ago, going back into the late 1800s. That was the thinking. Even in the mid 1900s, it was still thought that it wasn't really an ice sheet, but it was the glaciation was from an amalgamation of alpine glaciers forming large Piedmont glaciers that filled a lot of the valleys, but it wasn't an ice sheet. Then in the second half of last century, it was finally decided, well, we're finding these marks way up here on the sides of mountains that pushed ice all the way over into Puget Sound and out to the Pacific Ocean and blah, apparently it was an ice sheet, at least at its maximum for a little while after all. And in that case, it was very thick over everything in the middle of in the middle of central British Columbia and coming down into the Okanagan region in the United States. It wasn't just glaciers on the ground coming out of valleys. It was a more dome-shaped, roughly, ice sheet. But there's another alternative proposal more recently in the last 20 years that maybe it was actually thinnest so it would have been thickest over the Okanogan Valley if it's an ice sheet, according to those reconstructions in that theoretical model, because the Okanogan Valley is the low point in that area. And so to go up to the top of the ice sheet above that, that's thickest. But the alternative is no, maybe the Okanogan Valley was full of water. And so the ice sheet formed an ice shelf, a thin ice shelf floating on water in the Okanogan Valley. So even recently, after building up the evidence and the reasoning to understand that the Cordilleran Ice Sheet was an ice sheet, it's been proposed that nonetheless it was thinnest rather than thickest over the Okanogan Valley. Okay, well, one way to get perhaps something of a handle on that, I went out and looked at the tops of 3 high peaks on either straddling the Okanogan Valley on the United States side of the border, and that's Mount Bonaparte, which is over here, Moses Mountain down here, and Mount Tiffany Mountain over here. Here's a scale, so this is the United States version of or portion of the Okanogan Valley, down to where it comes into the Columbia River. So you can see the scale here. And these are the highest peaks in their area by hundreds or over 1,000 feet. they stick up above their surroundings. So these are good high points to see if the ice sheet was up over the top of them or not. So here's the top of Mount Bonaparte from when I visited it. We're looking east, so to the right here is south, and this looks glaciated to me. The granite there is relatively clean. It has lichen on it, but it's not totally covered with lichen. It's got a lot of fresh white color to it. And even more convincing, mixed in with the sediments and dirt in between the somewhat eroded and slightly shifted pieces of the bedrock up there are pieces of very different rock, metamorphic rock, slightly metamorphosed, that match an accreted terrain, a geological mass of rock from north of Mount Bonaparte going up towards the Canadian border. So for those exotic or erratic rocks to get there, they would have been brought by the ice sheet and brought up and left on top of Mount Bonaparte. So that's, to me, quite convincing that it was overtopped by the ice sheet. Another thing about these boulders is they're smooth on the left and steep on the right, or these outcrops. If they're still attached to the rest of the earth, these are outcrops. But that's consistent with the ice flowing from left to right, how it smooths and abrades the surfaces facing the direction the ice was coming from, and plucks out and quarries pieces of rock on the downflow facing sides. So the ice sheet, I think, was over the top of Mount Bonaparte at 7,257 feet above sea level. South of Mount Bonaparte is Moses Mountain, not quite as high, 6,774 feet, but the whole ice sheet is sloping, its surface is sloping down to the south. And I had heard when I lived in Omak from people that were interested in local geology that they had heard or thought that Moses Mountain was of interest because it was a nunatak that stuck up above the surface of the ice sheet. I'm not sure where they got that information. That was a long time ago. Just me and some people I met telling stories and so on. But when I went up there, I became convinced that it was apparently overtopped by the ice sheet. It was not a nunatak sticking up out of the ice sheet. And that includes, again, these relatively fresh white granite boulders, not all eroded and crumbly, weathered in place for longer than the ice ages granite, but relatively freshly cleaned up granite. And the boulders look moved around and stacked up on each other in some places. So now I didn't find exotic non-granite that doesn't match the local bedrock from up towards Canada, but for 20 or 30 miles north of Moses Mountain, it's almost all similar granite. So that might be why. So overall, I think Moses Mountain was overtopped by the ice sheet. I think these boulders, the way they look shifted around and mixed together and are fresh and not lichen covered and not weathered down to crumbly material known as grus, which is what granite breaks down to as it weathers. It was apparently glaciated. Okay, then there's Tiffany Mountain, which is the highest of these, 8,242 feet above sea level at the peak. And the top of it does not appear to have been overtopped by the ice sheet. So this picture, you're looking to the east up to the top of Mount Tiffany from a little ways below the peak, a few hundred feet. And the upper part of this, where the rocks are darker colored, dark gray, mostly, the rocks are highly angular. They're covered by lichen, up to really thick, crumbly lichen that you can break apart in your fingers, finger thickness kind of lichen. And it looks fractured because it's so angular. And it's all the same type of rock that looks like it weathered in place. Down below this break and slope, you get these white, again, relatively freshly exposed, cleaned off granite rocks that in some cases looks like the boulders got moved around some. I think that was glaciated down there. The ice sheet moved over it enough to clean it up, to clean it off and modify it and shift some boulders around. So that if that's correct, then the glacier, the top of the ice sheet was across here somewhere at its maximum. Okay. All right. So the implications of that are that the ice sheet was very thick in those areas. Even on Tiffany Mountain, it's still up to about 8,000 feet above sea level, with the very top of the peak sticking out above that. And if that's correct, so here's the reconstruction of the surface of the Okanogan Lobe portion of the Cordilleran Ice Sheet on the right. I took a portion of that map from John Riedel, 2017.
And he was reconstructing that mostly from other people's work. And, it's an approximation from what other people have put together from noon attacks and how the surface of a glacier is shaped from physics and from studying actual glaciers and their shapes. Anyway, these elevations of meters above sea level, 2,200, I think this would be 2,000, 1,800, etc. They're about 300 meters too low if the ice sheet in this area was over the top of Mount Bonaparte and Moses Mountain and almost over the top of Mount Tiffany. So it was very thick, I think. And that doesn't work if you have just a thin ice shelf sitting on water at the very bottom of the Okanogan Valley. The ice wouldn't have flowed from north to south across these mountains. It would have flowed down into the valley. I mean, the thinnest ice floating on an ice shelf on water in the bottom of the Okanogan Valley at last glacial maximum or near last glacial maximum, I don't think works. And also for the ice to be thickest over the valley, because the valley is the deepest part of the landscape and the ice sheet is domed over the landscape. That matches the evidence I'll show you later for how the last remaining ice or glacier parts of the glacier, when the ice sheet melted away at the end, were down in the bottom of the Okanogan Valley. And if that was just a thin ice shelf, that would have melted away first, not have been the last part of the glacier left at the end. Okay. So I mentioned that we would talk about, at least briefly, about the relationship between the ice sheet and the channeled scabland, which were created by these giant floods. We know that at least a lot of the floods that formed the Channeled Scablands came out of this body of water known as Glacial Lake Missoula, which was formed by a glacial ice dam, which we'll get to that on the next slide. But a mega flood is a flow of water, a discharge at or more than 1 million cubic meters per second. And that's huge. That's way beyond whatever any rivers in the world can do today since, in the last 10,000 years or so. So these are, as J. Harlan Bretz, who first figured out the mega flood origin of the Channeled Scablands, as he wrote, I mean, these are floods that boggle the mind. They go beyond human experience, and it's hard to imagine their force and their impact. But you see it on the landscape here. So in the background of this slide, the photograph is one I took. I don't think I gave the source here like I should have, but anyway, it's of dry falls in between Upper Grand Coulee and Lower Grand Coulee in north central Washington, and that's the biggest coulee, the biggest steep wall eroded valley cut into these layers of basalt by these mega floods. And that's right near, by the way, in the background at the top, at last glacial maximum, you'd be seeing the edge of the Okanogan Lobe. So that's a mega flood, and that's the Channeled Scablands. Over here is the Scabland area that just got stripped off of the soil and silt that was on top of it, but not eroded down into a coulee. And here's the channel of the Channeled Scablands, Grand Coulee, the biggest one of all. All right. What was the influence of the Okanogan Lobe on that? Let's look at this map. Oops. Didn't mean to do that. Okay, so the dark blue across top is the southern part of the Cordilleran Ice Sheet coming down across the Canadian border. Not that there was a Canada back then, but as we think of it now. And here's the Okanogan Lobe right here with the big red arrow and label pointing to it. Over in the Idaho Panhandle and Montana, okay, so over in the Idaho Panhandle, a lobe of this ice sheet came down and crossed the Clark Fork River and blocked this drainage out of northwest Montana of all the water. And so the water, and it was a, thick, deep lobe in a narrow, deep valley. So it made a nice ice dam that really backed this lake up deep and spread out into these other valleys in the Rocky Mountains in northwest Montana, all the way beyond Missoula. So this is Glacial Lake Missoula, this yellow color in here, backed up behind this glacial ice dam. But we know that apparently multiple times the water built up deep enough and enough pressure, it broke through the ice dam and went flooding across eastern Washington, down the Columbia River system, spread out into the Willamette Valley. It was so deep when it got there, and then overall it went out into the Pacific Ocean. Okay, and it formed this huge braided stream eroded landscape, the Channeled Scablands, on its way out, or at least that was one of the main sources of the water that did that. The one confirmed one that had a large volume of water that could explain that. In more deep, and so this orange color is channel scablands. Um, the Okanogan Lobe, once it crossed the Columbia River, that created an ice dam also. So what happened? The Columbia River flows, I think, like here and then down here. Okay. Well, it's that portion of the Columbia River, the little bend of the Columbia River up through here, where it comes down to Wenatchee and on south. That was dammed by the Okanogan Lobe once the Okanogan Lobe dammed the Columbia River. And at the maximum, the Okanogan Lobe here, the ice dam it formed was pretty near where Grand Coulee Dam is today. Okay. So that backed up another lake on the Columbia River, which is Glacial Lake Columbia. It may look pretty big, Glacial Lake Columbia, but it was actually relatively shallow and small in volume compared to Glacial Lake Missoula. But anyway, that's the Channeled Scablands. That's the Cordilleran Ice Sheet. Here's the Okanogan Lobe. So if nothing else, the Okanogan Lobe had an influence on which way floods coming out of Glacial Lake Missoula could have found their way across eastern Washington. Before it got there, if there were any floods coming out of Glacial Lake Missoula, they would have, most of the water, if not all of it, would have gone right down the deepest main part of the drainage, which is down the Columbia River. Okay. But once the Okanogan Lobe dammed the Columbia River, the water had to find other ways out if it was coming from Glacial Lake Missoula. So there's that influence. Okay, now I'm going to bring up that meltwater hypothesis I mentioned before from Shaw and others, 1999, and then a more detailed paper elaborating on how it may have worked and what the evidence is in their interpretation, their read on it for the Okanogan Lobe region by Lessman and Brennan, 2009. That is that idea that I heard about at that talk back in around 2012. Should have looked it up. I can't remember the exact year. One of the co-authors on the 1999 paper gave in Wenatchee to the Wenatchee Valley Erratics, a geology club there that's part of the Ice Age Floods Institute, etc. But anyway, this group that's interested in geology went and heard this talk. And I was floored by this hypothesis and I was fascinated by it. And then eventually I checked it out and I wasn't quite so floored by it in the end, as I'll show you. First of all, if you go back to that 1999 paper, the body of water that they propose, or at least speculate could have been there, the Shaw and others 1999 paper, they have it at 100,000 or more cubic kilometers of water volume. And that's that dark gray area on this map on the right, taken from that 1999 paper. Okay. Compare that volume of water to Glacial Lake Missoula, over 2,000, maybe 2,500 cubic kilometers. And here's Glacial Lake Missoula in here. So this is, many times bigger, tens of times bigger in water volume than Glacial Lake Missoula, which is interesting. The evidence for it, and this goes back mainly to John Shaw. He had a hypothesis that he pushed for much of his career, and he died in the 2010s. That drumlins, these streamlined, rounded ridges, we'll see a couple examples of later, that form under glaciers. He proposed that at least some of them, most of the ones he investigated, formed by giant subglacial floods. Okay, so there's a lot of drumlins and fields of drumlins in the Cordilleran Ice Sheet and the Okanogan Lobe landscape. So that was one piece of evidence. Those are from giant floods under the ice sheet, according to Shaw's interpretation, the meltwater hypothesis. The other is tunnel valleys. I skipped ahead to the next slide, but that's okay, because here's an image from the Lessman and Brennan 2009 paper, looking southeast, down the Similkameen River, Palmer Lake Valley, Thin Lehican Valley. Similkameen River actually today bends over this way, but these are tunnel valleys, so called, because they don't just go downhill in one direction. When you go down this way, they're partly uphill before they go back downhill. So the tunnel valleys are the other piece of evidence. So the meltwater hypothesis is that super giant subglacial flood came through, lifted up the ice sheet, and had to be at least as deep as the drumlins are tall and as wide as the drumlin fields where it formed the drumlins. And it also channeled through these valleys and eroded out, or at least further eroded out if they were already partly pre-existing, these valleys. But it pretty much says in the paper that that's how the main parts of these formed, is from these giant floods. And this is a big scale. So that's huge. All right, but I have looked into this. I was somewhat captured by it or intrigued by it at first because I hadn't heard of it before. Um, and it's so, systematic for explaining so much of the landscape. But looking into it, here's what I found. First of all, sediment, you can look at the sediment, and other people have done this, across the Channeled Scablands and out to the Pacific Ocean that was deposited by these mega floods, these giant floods. And in many cases, from the minerals, from the chemistry, from the isotopes, the particular types of atoms in them, and so on, you can track as to whether they came from apparently the Glacial Lake Missoula area, which is old Precambrian crust with a distinct set of signatures in its minerals and chemistry and atoms and isotopes, versus the Okanogan Lobe, which is younger and overall distinct from the Glacial Lake Missoula area in terms of the sediment types that would come from there. Glacial Lake Missoula dominates the sediments. It's hard to find examples of sediment in the Channeled Scablands that would have definitely come from the Okanogan Lobe, except right near the Okanogan Lobe. Even Glacial Lake Columbia, remember I showed that? That comes right up against the Okanogan Lobe itself. Even all the flood deposits in Glacial Lake Columbia, almost all of them, came from Glacial Lake Missoula, and only a few beds towards the end of the sequence came from the Okanogan Lobe next door, and those didn't have to be big floods. The Okanogan Lobe was so close, so this could be late, minor, sub-mega flood scale minor outbursts caused by the retreat of the Okanogan Lobe at the end. So I'm going on too much about this. The Glacial Lake Missoula water. Okay, let's back up a step. Back in the 1990s and early 2000s, theoretical models of take Glacial Lake Missoula and calculate how it would flow across the landscape. They were finding in these models that it didn't fill the Channeled Scablands up high enough to account for the highest level flood marks. Okay, how deep the floods got. So some water seemed to be missing, the missing water problem. Well, water coming from under the ice sheet, including the Okanogan Lobe, that would be the missing water. That would account for that. Some other water source seemed to be needed. More recent theoretical models, supposedly more advanced, have found that especially up near the ice sheet, that part of the Channeled Scablands, there's plenty of water from Glacial Lake Missoula. It fills in up there, including taking into account when the Okanogan Lobe was blocking the Columbia River and how the water would have been channeled and so on. Anyway, there's enough water to fill the Channeled Scablands up there. You don't need, in fact, you can't really have, at least not at the same time, extra water coming out of from under the Cordilleran Ice Sheet. Speaking of the Channeled Scablands, or no, wait, let me go back to the water source. Um, are you really going to get some huge amount, Glacial Lake Missoula size or a much larger volume of water on or beneath the Cordilleran Ice Sheet up there to the north, up to where the ice came from, the zone of accumulation where the snow wouldn't melt and the ice was frozen and flowing out from? No, in that zone, the climate was too cold and the glacier melts too slowly to produce that anywhere near that much water. There's been one paper by Livingston and others where they calculated how much meltwater could have been generated and existed under the Cordilleran Ice Sheet, including in the Okanogan Valley, and they find up to a few tens of cubic kilometers of water in the deep parts of what's now, the Lake Okanogan Valley in British Columbia. A few tens of cubic kilometers as opposed to over 100,000. I mean, you're not going to get these giant mega floods from that little bit of water, relatively little bit of water in the deepest parts of the Okanogan Valley up in Canada. That's not what the underburst model calls for. It undercuts the underburst model. I'm going to skip number 4, but let's just say there are other, I think, more plausible explanations for how the drumlins and the unusual valleys of the Okanogan Lobe formed. Okay, so let's get to that. I told you this was a long talk, didn't I? Let's go over these 4 categories of landforms. The drumlins and other elongate streamlined bed forms that formed beneath the ice sheet. These unusual valleys that don't just go downhill in the downstream direction like a normal stream valley would. These unusual valleys that formed in response to the glaciation somehow. These terraces, these flat top benches along the sides of the valleys. And then another thing that may be less widely known, which are glaciotectonic features, including what are called hill hole pairs. Okay, let's start with the drumlins and other elongate, streamlined looking bed forms. Here on the right, I took a picture standing on a drumlin on the Waterville Plateau in north central Washington. Off in the distance, the horizon there is the lumpy parts of it. That's the Withrow moraine. That's as far as the ice sheet got, and it left a pile up of sediment there. And that's a few miles away. So to the right, drumlin number two, D2, you can see more of the shape of a drumlin. Okay. And down at the bottom, you can see a sideways view of the shapes of these drumlins. And okay, so D1 is the one I was standing on. Look, here I'm on the crest of it looking south. Here I'm off to the side of it looking west. Where's my pointer? Um, Here we go. Yeah, so here's a profile of drumlin number one. Classic drumlin shape, nice and smooth and rounded and elongate. Some of the evidence I saw, and also reported by other people who have looked at some of these drumlins on the Waterville Plateau, including Isles and others, anyway, is that they are cored, at least in some places, they appear to be cored by bedrock. They have bedrock, which is basalt in this area, inside. So these are partly eroded off and reshaped basalt, if that's correct. There are, in places where the bedrock is exposed, there are glacial striations on them. Because when an ice sheet is flowing across a surface, which would also be with the aid of a bit of water at the base of the glacier to help lubricate it, but nonetheless, the ice is flowing right across the Earth's surface. The bottom of the glacier is full of pieces of rock and even boulders, and you got the weight of hundreds or in most places thousands of feet of ice sheet up above you. That's a huge amount of weight. That's quite the sandpaper scraping across the bedrock, and that leaves these scratches in the direction, showing the direction the ice was flowing, called glacial striations. There's this diamicton, this mixed boulders down to sand and clay size. Um, if it does go down to clay size, it at least goes down to sand size here. That is probably glacial till left from the glacial ice. Sediment moved and then left in place by the glacial ice. So my conclusion is these drumlins make sense in terms of being formed by erosion by the flowing ice and redeposition downflow of some of the eroded material. Okay. Not from giant subglacial floods. Here's another way of looking at considering how these elongate subglacial streamlined bed forms originated. So this image from Google Maps, it's, about 100 miles wide. Lake Chelan on the left or west, north to the top. Here's the Columbia River. So the Withrow moraine is along and just behind this white line down here. Hang on, get rid of my own controls on the computer so I can see what I'm pointing at. These yellow lines are just showing the general trend of drumlins and other elongate subglacial bed forms that were formed either by the ice flowing along or by giant subglacial floods flowing along. And the Waterville Plateau is here up to the Columbia River. And so between the Withrow moraine and the Columbia River, that's the true lobe part of the Okanogan Lobe. But the Okanogan Lobe corridor goes on up into Canada along the Okanogan River at its center. Up here on the Omak Plateau, north of the Columbia River, there's some more drumlins and other elongate bed forms trending in these directions. The Waterville Plateau, the bedrock, the solid rock under the surface, is all Columbia River basalt flows nearly or at horizontal position. Same thing on the eastern 2/3 of the Omak Plateau. Okay, but if a giant subglacial flood formed these drumlins here coming down to the Withrow moraine, it would have had to have spread out like the directions of the drumlins do, and it would have to be a flood of turbulently flowing water filling that area under the glacier, flowing along at least as deep as the drumlins are high, powerful flow, and then it would have had to disappear. Because beyond those drumlins, you come to the Withrow moraine, which show no sign of water flow like that. And beyond the Withrow moraine are these hills made of wind-blown silt known as loess. So that alternative hypothesis runs out of steam right here, as far as I can tell. And if it doesn't work there, why does it work? Do you have to go further north and then apply it there? and those papers do mention the drumlins on the Waterville Plateau, especially Lessman and Brennan in 2009. I brought up the basalt under here, under most of the Omak Plateau and all the Waterville Plateau, because the Channeled Scablands are formed in basalt. We know they're formed by megafloods beyond, south of where the ice sheet was. Um, and we know what kind of landforms the megaflood formed in and from the basalt. Uh, and you don't find those landforms formed in the basalt on the Waterville Plateau or the Omak Plateau. Why not? I think because there weren't such giant floods there. Is one way to conclude from that, probably. Okay, let's go on with these glacially eroded, or yeah, that's my interpretation. Probably shouldn't have labeled it that way, but here is some eroded bedrock, an eroded bedrock surface at the entry to Whistler Canyon, which is just south of Oroville in the Okanogan Valley. So, and we're looking more or less east, so flow direction was to the right, to the south. If you look closely, there's lineated, streamlined bed forms, maybe glacial striations along these surfaces. And this is not drumlins; these are other streamlined subglacial bed forms that have smooth surfaces on the sides, and in some cases straight surfaces on the sides facing the direction the ice would have been coming from, and then steeped sides on the downflow facing sides of these features. That's consistent with how flowing ice abrades like tremendously powerful sandpaper the 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 sides that face towards the flow or are parallel to the flow, and then variations in the pressure of the ice and the water down there. There is water at the base of this glacier. For it to flow that much across the surface, it had to have the lubricant of water. Anyway, variations in pressure help it crack out and pluck out and take away pieces of rock from the downflow side where it's coming off the face of the rock. That's been seen from observations, and it also matches, theories of how the ice would erode these surfaces. Okay, here's another example of a subglacial landform that was probably formed not by giant floods, but by flowing ice primarily. There was water involved, but not giant floods. So this is, if you go just north of Omak on Highway 97, park and look off to the east, you'll see this big ridge, or this elongate streamlined form across the Okanogan River with some of those terraces down at the bottom, but those are sediments on top of the bedrock that we'll get to later. Here's the bedrock feature up here. It's a roche montagnais. The side of it facing the direction, and it's all bedrock. It doesn't have a bunch of sediment on top of it up here. The side of it facing the direction the glacier came from is smoothed off and abraded. The downflow side is all steepened into cliffs here on the right. So that's a roche montagnais. Okay, let's wrap up these drumlins and other elongate streamlined bed forms. They are from glacial erosion. I think you can make a solid case for that in each of them, and there's places where you can rule out a giant flood origin. The evidence includes the smooth, streamlined Stoss sides. That's the side facing the direction the ice came from, and then steep lee sides, direction the ice was flowing towards, facing the ice downflow direction. Here's a picture of Omak Creek Valley. In this case, the flow is to the left, so you have smooth, streamlined slopes coming up from the right, up to the left, and then the steep slopes facing to the left, facing downflow. Now, I don't have pictures of this. I had some from Google Maps and Google Earth I could have used. But if you look on those satellite photos, you'll see places where these elongate streamlined bed forms go right over ridges and right down the other side in ways that flowing water would not do. And, nice parallel lineations on a landscape scale. Till and erratic boulders are in and on and around these features. The till and boulders are directly from glacial ice, not from flowing water. And there's striations on a lot of these surfaces, glacial striations. Okay, let's switch to the category number 2 out of these 4 categories of glacial landforms, which is tunnel valleys. Tunnel valleys, like I think I said, maybe I didn't, that's a valley that has an uphill slope in the downflow or downstream direction, okay, which is not how a normal stream valley works. Streams are formed by gravity pulling water down channels on the Earth's surface, and streams on the Earth's surface overall can only go downhill. So you need something else to get it to go uphill, such as the pressure of all the glacial ice up above pushing on the water under the glacier, and that hydraulic pressure can push water uphill for significant distances that in ways that you can't get without that extra hydraulic push from the weight of the glacier up above. So here in this image of the Omak Plateau, just north of the Columbia River, so you have on the left the Okanogan River coming down and joining the Columbia River on the bottom left. Just out of view towards the top are the towns of Okanogan and Omak. Over on the right, we have the Omak Lake Valley, and next to it, branching off of it, the Goose Lake Valley. And here's Soap Lake Valley, which comes up and has Soap Lake in it and drops back down. It's a little bit hard to see the three-dimensional shape here, but there is a valley coming through here, the Soap Lake Valley. And there's a whole bunch of smaller valleys that we don't see the details of on this view, but they're in there. So I put in some, TV tunnel valley indicators, including these little notches cutting through this ridge here. So there's a variety of shapes and scales of valleys here that were under the ice sheet, which have as part of their length of the valley, they partly go uphill. Okay, like the Omak Lake Valley goes down into the base of Omak Lake, and then it comes uphill going down in the downflow direction to the southeast back out of the lake, down and up. That's a tunnel valley. Or up here, the ridge crossing ones, they go up the ridge and then they go back down. And in one valley, that's, they have an upflow aspect, an uphill aspect in their downflow direction. A few things to point out. The Soap Lake Valley and the Omak Lake Valley and the Goose Lake Valley are they're along fault zones. Fault zones, they can be places where the water erodes more easily, but they're especially known to be places where glacial erosion, can be concentrated and do an extra amount of, deep erosion. That's one thing. Let's go on and look at, so here's the side of Omak Creek Valley, which is up here. So it's part of the Omak Lake Valley overall. It's the main valley coming in from the bigger valley coming in from the north. And you're looking to the east, so to the right is south, so that's the flow direction is off to the right. And this looks like a glacially eroded landscape. You have smooth, streamlined surfaces on the Stas side facing the direction the flow would have come from, and these plucked steep surfaces on the downflow facing sides, the lee sides. Okay, that's what I talked about earlier in those streamlined subglacial bed forms. This is nicely consistent with glacial erosion. Here's a more detailed look at some surfaces going down that same valley into, here's Lake Omak itself, or Omak Lake. I always get them turned around. These are glacial striations showing how the ice was flowing along the surface of the bedrock, eroding the bedrock. Okay. So in summary, I could go on and on about the tunnel valleys. There's a lot of other valleys to look at, a lot of complexity involved, they actually originated in a variety of ways, depending on which, when you put them all together, all the ones that have been designated as tunnel valleys are having an uphill slope in the downflow direction, or having a lake in them where they got over deepened along part of their length. So I'm just going to have to summarize it here and then move on. I want to back up though. The word tunnel valley is often assumed to mean that it originated by flow of water in a subglacial channel. Okay, so you got to be careful with that word. If you use that word, you may be assuming a conclusion already as in terms of how the valley formed. Just to use that term, you've already interpreted its origin. However, in the Okanogan Lobe, a lot of valleys that have been pointed out as being, in some sense, tunnel valleys show strong evidence of erosion by glacial ice. I didn't point out that, for instance, the Omak Lake Valley, if you take a landscape profile of it going across the valley, it's got a U-shaped profile, which is consistent with erosion by glacial ice. So for the most part, anyway, the erosion of Omak Lake Valley, I think, was by glacial ice, at least not by gigantic flows of subglacial water. There was water at the base of the glacier. That was a wet base glacial zone, warm base with water at the base, but not giant floods. And moving on, many of those small ridge crossing valleys, A lot of them follow the jointing or crack systems in the rocks. That a lot of those, you go look at them and they have glacial striations in some cases. Those could have been eroded out by glacial ice. Okay. Um, and then there's a lot of valleys along the side. A lot of these smaller stream valleys are up on the sides of, say, the Okanogan Valley or the Methow Valley, the larger valleys, and they cut through ridges and they work their way along the sides of the big valleys, sloping down the side of the valley and eventually joining the main valley in ways that make sense with the ice sheet. When it went away, it was melting and shrinking to with less thickness, getting thinner. So it was lowering itself down in the landscape and blocking off stream drainages coming into the main valleys. So the meltwater and whatever water was coming down off the landscape was blocked by the shrinking glacier filling the rest of the valley, and had to find a way out across the landscape parallel to that or off to the side. And in many cases, those were probably subaerial, beneath the air, not beneath the ice, streams that were draining the side of the area off to the side of the valley when the glacier was still filling the rest of the valley from there on down. Okay. And that there's a lot of those that have been interpreted that way by others in the Okanogan Lobe and Cordilleran Ice Sheet. And some of them have uphill slopes along part of their length, but that doesn't mean they couldn't have been formed by this side valley outside the glacier drainage system, at least to some extent. There are some streams or rivers, including bigger rivers such as the Similkameen River, that were diverted or captured or had where they drain out shifted significantly by the effects of the ice sheet, and it would dam off parts of that valley while other parts were open. And so that once the glacier was gone, the new route that the water had been forced to find became the new route up until now. And there's an old abandoned part of it beyond that. So there's those kinds of valleys as well that are not necessarily tunnel valleys that form only by flow of water under the glacier. I'm going to skip down towards the bottom. So nonetheless, under this wet base part, under the warm base with water underneath the ice part of the glacier, in some cases it was more than a film of water, especially as you get further and further towards the margin of the glacier. You're getting more and more meltwater, some of it under the glacier. And so there would have been some channelized flow of water under the glacier in places, forming or at least helping form some of these valleys. But with all these other ways that the valleys formed, not just from some glacial channelized water flow, it's hard to separate out the ones that are true tunnel valleys in the sense that they did form by subglacial channelized water flow. And so I could go on about these, like I said, but the ultimate thing to say here, as far as the big ideas that I'm testing, is that there's no mega flood scale underburst needed to form any of these valleys. Okay. We're on to the third landform category out of 4, so we are moving along. This is the terraces, the flat top benches along the sides of the valleys. So this picture at the bottom right shows the southern end of the Okanogan River almost to where it meets the Columbia River, just out of sight beyond the bottom of this image from Google Maps. And you can see these flat top surfaces to the left or west side of the Okanogan River here. These are part of what's called the Great Terrace. This is part of what's called the Great Terrace, which runs at approximately this level above sea level, way up past Omak to the north, and way down along the Columbia River to the Chelan Airport area, nearly Chelan Falls to the south. So that's something like 100 miles, or that sort of order of distance, maybe more, that this Great Terrace runs. It's a little bit discontinuous, but for the most part, you can pick it out along the northern and western sides of these valleys, Okanogan and Columbia River valleys, all the way down there. That's drawn attention from geologists trying to figure it out for over 100 years, since the late 1800s, this Great Terrace question. Now, to get terraces like this along a stream or river, there's 3 main possibilities. One is that they were deposited by underbursts under the ice sheet. I bring that up because that was proposed specifically by Lessman and Brennan when considering if there were underbursts, as they were suggesting, where would the sediment have gone? These huge amounts of sediment. One place they proposed was into the Great Terrace. Okay. or they could have been deposited, these flat surfaces filled with sediment underneath. That could have been the floodplain, a filled-in floodplain of a river drainage system draining a retreating portion of the glacier, the ice sheet that was back up to the north somewhere, maybe just on the edge of this picture, a whole bunch of meltwater coming out. That would have filled in the valley from side to side with sediment, making a valley train or a floodplain below the glacier. Um, and then subsequently, the river and lower flows of water and lesser amounts of sediment cut down into it and uh, incised it and made a lower terrace, and then finally you get the modern Okanogan River. So that's another possibility. The third possibility is that the Great terraces like it, were deposited next to the remnant of the ice sheet that was filling the rest of the valley off on the right. Okay, so there was this space between the side of the glacier here and the side of the valley here. And so meltwater coming off the glacier would spread sediment into here. So would water coming down from the streams that came into this valley from the side. That would have spread alluvial fans and so on into this zone between the ice sheet and the valley side. So that would be a kame terrace, Kame, deposited along the side of the glacier, between the side of the glacier and the side of the valley. And as I'm going to show you a couple pictures of some of this evidence, the presence of kettles, which are roughly round-shaped, smooth-shaped holes in glacial sediments where large blocks of ice were left by the retreating glacier, and more sediment came in and filled in around the block of ice before it finished melting away. So you get a hole left there from where this chunk of ice melted. There are quite a few kettles in the surfaces of these terraces, including the Great Terrace. Glacial erratics are around the edges of or in these terraces in some places, deposited right there by the ice as it was retreating away from that spot. Glacial till is found interlayered in some places with the terrace deposits, and that's from the glacial ice itself. And there are other ice contact features, including distorted beds from when the ice melts away or chunks of ice melt away from within the sediment pile. Then the beds of sediment that have already accumulated, they have to shift and deform and slump. And there's ice contact features like that in the Great Terrace and then these other terraces. So I come down agreeing with most previous studies on the Great Terrace and other terraces along with it in these Okanogan Lobe valleys, that these are kame terraces deposited alongside the retreating, shrinking ice sheet that was still filling parts of these valleys. Here's a picture into sediment exposed from the side, along the side of one of these terraces, looking at east of Omak, by the mill there. This has been interpreted by Menard in a map of the glacial deposits from 1985 as advanced outwash. So these are beds of sand and gravel with glacial boulders that are rounded off, or cobbles and so on, some boulder size, slightly into boulder size, nicely rounded from up north. So these were brought in by the glacier and then spread by meltwater coming off the glacier at different energies, where the water was not so energetic and it was just spreading sand like in here, maybe in a channel that cut into somewhat the previous sediments underneath. Anyway, nice glacial outwash features. And then on top, Menard interprets that as till from when the glacial ice was sitting here and then left its unsorted, unbedded mixture of materials behind. Okay, so nothing like a giant flood deposit, and also not like a floodplain beyond where the glacier was. Okay, the glacier was here, and this is outwash and glacial till. Here's another picture, a little bit blurry, of the side of the into the side of one of these terraces. And what we have, it's hard to see here, so I drew some lines, but there's fine grained sediment, sand to silt to maybe even clay, that might have accumulated in a lake or a delta surface where sediment's spreading out from a stream into a lake. Anyway, these finer beds of sediment have been, they originally started out pretty close to flat or not sloping very steeply, but now they're all contorted up beyond vertical I think there's a fault in here. There's lenses of gravel in here too. And over on the right, there is a irregular body cutting into the sediments underneath with bouldery, unbedded, unsorted sediment like glacial till. I think these are ice contact features. I'm not sure how plausible this is, but if this is glacial till, maybe there was a chunk of glacial ice sitting within this body of sediment that you're seeing evidence of right here, now exposed by erosion. And with all the ice melting away from this vicinity, the previously deposited soft beds of sediment could have slumped down in response to losing those buttresses of glacial ice that were once next door to them. Okay, here's one more picture. This is northwest of Brewster, where Swamp Creek is opening up into the Columbia River Valley. And this is looking west, so south is to the left. And also the bedding in these deposits here tell us that water was flowing from right to left. So the flow direction is to the left. But at the bottom of this pile, there is a big pile, base of unsorted, unbedded boulders to clay, which looks probably like glacial till up to about here. And then it's overlain by sand and gravel beds from flowing water. This might have been where water coming down Swamp Creek encountered a temporary lake in the Columbia Valley with the glacier off south of here, remaining part of the glacier just south of here in the Columbia River Valley. And so the water was spreading out into a lake and forming these beds of sediment, perhaps, or else just spreading the sediment into flat ground as it came out of the steeper valley to the north. And so it's been posed by the underburst hypothesis proponents that perhaps these were underburst deposits from giant floods coming down from the north, but they're not that big. The rocks aren't that big. They don't have the right type of bedding to match giant flood deposits. They've also been proposed to be rhythmites accumulated in lakes where backflows, like a giant flood goes into a lake and goes up a side valley and the water slows down and it puts out silt and clay, sand and then silt and then clay. But these are not that fine grained. These are gravel and sand. So I think it fits more that these are flows of water coming down Swamp Creek into a glaciated landscape in the Columbia River Valley that could have been subaerial flows, not subglacial flows coming down Swamp Creek. Let's see. I might have to do something here. Okay. All right, let's move on. One more thing about the terraces, and then I'll conclude it. This is looking up Swamp Creek a little bit further northwest from Brewster, up a little more towards its headwaters, off in the distance. And I put red arrows pointing down to terraces along the sides of this drainage system. That's consistent with the ice sheet when it melted away, getting thinner and thinner, lower on the landscape, and then pausing for several years at certain positions, and sediment would accumulate between the side of the glacier and the side of the valley. And then it would shrink, melt, go down lower as it went. These descending levels of terraces that you see in these valleys correlate with those streams that are usually interpreted by previous geologists as having been flows of water on the landscape outside the glacier when the remaining parts of the glacier were blocking the main valley. Okay, so there's a correlation between those two types of features, consistent with how the ice sheet wasted away by thinning down onto the landscape. So in conclusion about the terraces, I think they're came terraces deposited at least along one side in contact with the glacial ice and with a lot of glacial meltwater coming out into them. But they're complicated came terraces, like especially the Great Terrace, which you have another picture of up at the top, just north of Brewster on the side of the Okanogan Valley. Because sediment was also coming in from side valleys into this zone between the glacier and the side of the valley. It was not just meltwater coming off the ice sheet that spread the sediment into these came terraces, and in particular the Great Terrace here. And also there were times when the remaining parts of the ice sheet dammed the drainage and formed temporary lakes. So you get some lake bed sediments in parts of the Great Terrace as well. And here's the whole list of evidence that I think makes this a pretty conclusive case, at least in my read, on the origins of these terraces, including the Great Terrace. All right, so we're getting towards the end, except for that one weird topic of glaciotectonics. Let's apply what we've learned so far, or what I think I've learned so far, into a sweeping landscape interpretation. This is a Google Earth image here at the top from satellite imagery with north to the top right. This is about 20 miles wide from left to right, west to east, centered around approximately Winthrop, Washington, in the upper or towards the upper Methow Valley. Um, and along the bottom, I had Google Earth produce a topographic profile showing the ups and downs of, if you're looking sideways at it, the three-dimensional shape of the land in terms of, up and down three-dimensional look or third dimension look. And it's an exact, the vertical scale there is exaggerated to stretch the ups and downs out and really bring them out where we can see them. And that's along the white line here that runs across the whole image. That's where this profile, this shows you the ups and downs on that landscape along that white line. Okay. So I mapped it out in simple terms. Way off to the west here, where there's a lot more trees on the mountains and all those ridges and peaks, there's not much sign of any elongate streamlined bed forms having been eroded and shaped by the glacier flowing along. That could be because it was high up, colder, not enough water at the base of the glacier, not enough focused flow into a valley or whatever it takes to get the ice to move fast enough to cause that erosion. Okay. At least that much erosion, you can see the features from this far away. So that's zone A, high mountains, little erosion by the ice sheet, also marked down here. Okay. But then you get to zone B, where maybe in the slide from your viewpoint, it's hard to see, but if you could look at the original imagery and blow it up, you see elongate streamlined bed forms in this area. Okay. Mostly shaped into the bedrock, but I've been there, and my wife and I went there recently, just a week and a half ago, or almost 2 weeks ago. And some of these are partly reshaped into glacial till and glacial sediments, but mostly it's onto the bedrock by erosion by the glacier, I think, that form these streamlined bed forms in zone B. Okay. And you get a repeated pattern coming in from the right, from the high mountainous area, not so streamlined and eroded looking by the glacier. But then you get this zone where the glacier was apparently flowing faster, and did more modifying and eroding of the bedrock underneath. Okay, and then you get zone C down here, this relatively flat area, southwest and west of Winthrop, which is the Twin Lakes area, and that's full of glacial drift, glacial sediment, including glacial outwash and some glacial till, as if the retreating ice sheet stopped here for a while and spread a whole bunch of sediment out and left some till behind, and also left some chunks of ice behind that form these two kettle lakes, twin lakes. Okay. So this isn't bedrock. This is glacial outwash from the meltwater spreading sediment out, coming originally from the glacier nearby, and glacial till from where the ice was, just leaving its pile of rock material and down to fine grained sediment material behind. Okay. And then finally, after the glacier left, up until today, the rivers have been flowing through here and slightly re-eroding and re-spreading that sediment to make the modern floodplains that we have now. That's zone D. All right, so that's a simple interpretation of the landscape. One other thing I want to point out is the tunnel valleys, including, so let's see, here's Patterson Lake, west of Winthrop on your way up to Sun Mountain. But if you could really see the landscape, part of the valley system here comes out and goes into Elbow Coulee, following this path that I'm showing with the red mouse pointer here, highlighter. Okay. And I think it's called Elbow Coulee because it makes these sharp bends, especially this one right here. Not like a normal stream valley. And it's just about flat and even has some slight uphill slopes along its length. So that's the tunnel valley in the sense of having some uphill slopes. That's been interpreted by some previous geologists as having formed alongside but outside the glacier when the glacier had retreated to a remaining mass of ice in the middle of the valley here. All the water on the landscape next to the glacier had to find a way out. So for a while, it eroded out and formed Elbow Coulee. Okay. And then it retreated more, and other coulees. There's actually other coulees that are consistent with the ice shrinking to a narrower, more central part of the valley, and a new drainage system developing further in, closer to the glacier.
Although it's also been proposed that Elbow Coulee in particular might have formed under the margin of the ice. The ice might have been just over here, and water got under the glacier, and with the weight of the ice on top, that could have helped squirt it, or hydraulically force it uphill along part of its length. That's unresolved. Um, and that here is Peregrine Lake State Park. That's also a trough that goes up and then comes back down. So it's a tunnel valley in that sense. Again, most previous interpretations have this as meltwater outside the glacier when the glacier was blocking drainage through the main valley. So the water had to find a way across the landscape outside the bottom of the valley where the ice still was. And if you go look at Peregrine Lake State Park, like my wife and I just did a few days ago, you see all these streamlined subglacial bed forms, elongate subglacial bed forms, and they're quite convincing, and they're quite beautiful, and they have glacial till on them, and they have those shapes that are consistent with erosion by glacial ice flow. So I think, at least to a large extent, this trough here was formed by erosion by glacial ice. It may have had water flowing through it outside the glacier when the remnant of the glacier was blocking the rest of the valley. And it may, at one point, when the ice was flowing through here and eroding, there may have been enough water under here to get some channelized flow of water under the ice to help evacuate sediment and help it erode even deeper, like where Peregrine Lake is. Complicated. I told you the tunnel valleys are complicated. I always talk too much about them. So let's go on to this one. So this is just northeast of Omak, north of Omak. Womack's out of sight to the bottom left a little bit. Oops, I keep doing that. This is mainly Pogue Flat, another terrace. These terraces are locally called flats from up in the Okanogan all the way down to Wenatchee, where they were formed by giant floods outside the glacier. But anyway, here's a glacially related terrace up here that's mostly Pogue Flat. The northern part is called Poverty Flat, etc. But anyway, let's just call it Pogue Flat. This is about 12 and a half miles across from west to east, left to right. Again, along this white line on the bottom of this image is the vertical profile, the topographic profile showing the ups and downs in that landscape along where that white line is. Okay. So on this landscape, I don't see mountains high enough or whatever it takes to get a zone where the glacier did not erode and streamline the landscape underneath, including the bedrock to some extent. So over on the left, going up into the highlands here, there are elongate streamlined bed forms, GSB. So I show them down here on the profile as well. But here, see where the white line comes in, comes down off the bedrock uplands, goes across part of this filled in with sediment flat area, which is right here. Okay. That looks like outwash channels. If you look in more detail on the original imagery, zoom in and study it. These look like outwash channels. They have these channel and fanning out patterns of sediment from stream flows, water flows coming down Johnson Creek and spreading out onto the flats. Okay. But then from here to here, it goes up over some bedrock again, and you have elongate, what are they called? Glacially streamlined bedrock through here. I mean, it's hard to see in this image up here, but the topographic profile down here shows you it goes back up into the bedrock cored hills again through here that were shaped by the glacial erosion. Then it drops back down to Pogue Flat from here to here, where it's relatively flat. And here the white line crosses a couple of kettles that had chunks of ice in them and are partly filled with water. These small kettle lakes here. I didn't draw it through the big kettle lake. But anyway, these are kettles from chunks of ice that were left in the sediment as the glacier retreated. And then it drops to a lower terrace here. There's a little escarpment along here, and then a lower terrace, and then the modern Okanogan River since 12 or 13,000 years ago, when the ice sheet finally left the area completely, and there were no more effects from the ice sheet up to the north either. You get the modern Okanogan River and its modern flood valley confined down in here. And then it goes up steeply into the Okanogan Highlands on the east end after crossing some narrow terraces on the way up. And this is one of those tunnel valleys
from the north, it's coming up over this ridge, and then it goes through and drops back down. So it has an upward sloping part before it comes back down. All right, and there's a tunnel valley over here too. You can see my, I know, right here with this, and I can tell it's a tunnel valley because it has a lake in it or a pond, showing that it goes down into the pond and comes back up out. So it's slightly over deepened with an uphill slope if to the bottom left is the downflow direction. This could have been simply from erosion by glacial ice. Maybe this one too. Maybe this had some water flowing more than just helping lubricate the glacial ice. I'm not sure. Again, those tunnel valleys are complicated, but they don't require giant underburst scale floods to form. Okay, one more subject, and then we'll wrap it up, which is glaciotectonic features. So glaciotectonic features are large slabs or chunks, to be non-technical, of the earth underneath the glacier or ice sheet that got removed all at once en masse, giant chunk, and transported some distance and deposited by the glacier. Not a boulder at a time, not even a huge boulder at a time. Beyond that scale, like up to miles or even tens of miles wide, some glaciotectonic masses are that big. All moved as giant chunks out of the earth and slid and then repositioned by the glacier. So the Pot Hills on the Waterville Plateau have been identified as what we now call a glaciotectonic feature. He didn't use that wording, but identify Larry Hansen, in his PhD dissertation in 1970, studying the Waterville Plateau and its glacial features and how it related to Moses Coulee, which I haven't talked about, and I'm not going to, at least not yet. Anyway, the Pot Hills are a bunch of basalt that got taken out of the ground up to the northwest and moved a couple miles or so and shoved into place here. Not one boulder at a time, but as either one huge slab or several, large slabs. The Pot Hills overall are roughly a mile long and at their widest about a mile wide. And State Highway 172 runs right through them, east to west, headed towards Mansfield off to the left, off to the west. So you can go look at them, and some of you may have driven through there yourself already. So that's been identified as glaciotectonic, possibly since 1970. In 1994, Richard Waite wrote a field guide, the Geological Society of America, in which he went over the Pot Hills again, like Hansen had. And Waite also pointed out that the Burke Hills, a few miles that way to the west of Mansfield, also looks like a glaciotectonically transported mass of basalt on the scale of approaching a mile wide, or 2/3 of a mile anyway. And then even further down the highway, you drive straight towards Lone Butte in front of you heading west, and the highway has to curve around it. And that has also been identified, at least by Richard Waite, as transported out of a hole to its north by being shoved by glacial ice, not one boulder at a time, but by pretty much the whole thing at once. How can that happen? Well, when the ice is moving and it's a warm base glacier with water at the base, if the water pressure under the glacier gets high enough to where it's equaling the weight of all the ice up above it, then that reduces the friction, down towards maybe not quite zero, but it greatly reduces the friction. So if there's water in layers of the earth material under the glacier, in this case, the basalt, and in between these basalt flow layers on the Waterville Plateau, especially underneath just a few of them, there's a known layer of silt and clay and sand in between the basalt beds. If that got full of water at pressure equaling the weight of what was up above it, then it would not defy logic for the shearing force of the glacier and its steeply sloping surface up above to provide all that shearing force, and the glacier itself sliding along up above to shift a whole slab of the basalt right out along that plane of failure charged with high water pressure, very slippery material in there too, if it's silt and sand and clay. And really it would not be defying logic to move these large chunks of basalt up to a mile wide or whatever the scale was in terms of glaciotectonics. Each of these correlates with a hole in the ice upflow direction. Each is connected to a hole by elongate streamlined bed forms showing which way the ice was flowing. So there's this, and the holes and hills have similar volumes I'm going over the evidence for why these are glaciotectonic and not just some. These are not mesas of basalt in place that didn't finish getting eroded away while the surrounding landscape did. These were shifted by the glacier itself in large slabs or pieces at a time beyond the boulder scale at the glaciotectonic scale. What else did I mention here? And so when you go look at these, they're you can find partially intact portions of slabs of basalt in some of them, but not continuously through them. Mostly they're broken up basalt, boulder, and rubble that's just falling out of the hillsides. Because apparently during transport, the Columbia River basalt had such, you may have heard of the colonnade and the tablature, the way the basalts cooled and cracked apart when they first formed these amazing jointing or crack systems in them. And then if they're being shoved under shear force at the base of a glacier, or maybe in some cases in front of a glacier, along those joints, the rocks are going to break apart and shift and turn into boulders. And then you look at these hillsides and you can see the boulders eroding right out. Yeah, okay. And then surrounding these hills of glaciotectonically transported basalt are intact solid basalt flows at a lower elevation. Here is a picture. If you can make this out, pot hills are at the bottom right. And here's the 1 mile scale. These rectangles in red are a mile across because that's the spacing at which they lay out the county roads. And also the spacing of the township and range system on the topographic maps. Anyway, that's a mile. So this whole thing is a little over 5 miles across, about 5 miles across. Pot hills again are on the bottom right with a different view here. Here's State Route 172 headed west off to the left towards Mansfield, a little ways off the picture. And the green color is put in there using CalTopo software to modify this topographic map. The darker green, the steeper the slope. So it just brings out a little bit three-dimensionally the landscape features, even if you can't see the contour lines that show the shape of the Earth's surface. So here's the pot hills down here. Here's the whole area they came from, and they're pretty convincing holes that go down pretty deep if you go drive up the dirt county road and look at them. And they're right up the flow direction from the pot hills, okay, about 2 miles away. Here's the Hook Hills, and the Hook Hills and Wheeler Hills and Pearsall Hills, their holes are just about right next door to the hill piles. Okay, they didn't get shoved so far. They came out of higher level basalt escarpment back here and out of holes in the ground and got shoved up in these directions. Okay, and I've been to these, and my wife has been with me to a couple of these. We didn't go on the private property parts of them, but from the roads and nearby, we were able to get a pretty good look, and they're neat features. And they're convincing when you start thinking in terms of glaciotectonics, how that worked. Okay, here's a couple detailed views using, I think, Google Maps, and looking down and from the side. So these are less than a half a mile in length from left to right. There's a scale there. I arranged these so ice flow direction would have been off to the right in both cases. So you have a trough with a what's called a paraxial, or along the parallel to the axis of the trough, but along the side. These ridges along the sides of the trough. And then at the downflow end of the trough is a pile up of basalt, a hill complex. This one's a little bit bigger than the one on top. So you have a nice trough. You can kind of see the trough better in the way this image is shaded. Goes down into a hole deep enough to have a pond in it, and then it comes up into this hill, and it's a little bit hard to see how much this hill is piled up against it above the surroundings, but it's on the order of 100 feet, this little hill hole complex on a Waterville Plateau. Okay, I got to wrap it up because I'm running out of battery here. My computer, I'm almost there. Here's a big hill hole pair. Here's the hill, bottom left, about a mile, almost a mile across. Here's the hole to the north that partly matches the shape of the hill, like a jigsaw puzzle, which is interesting. Here's some of those elongate streamlined bed forms coming in. Let's see, what am I hooked up to? So I don't want to mess up my system here, but I got to put a battery charger on here. Okay. I hope I didn't interrupt it. Anyway, like here, there's an elongate streamlined bed form. There's a bunch of lineations like this, elongate streamlined bed forms, connecting the hole to the hill, the down ice flow direction. So I think this is a glaciotectonically transported hill or raft because it's almost flat and partly retaining its original shape of when it was in the ground, shoved out of this hole up here. Okay, pretty impressive. I've been over this raft and walked around. It's an interesting place to go visit. I went in the hole too. Um, one more example. This one is perhaps kind of cute, as it were. This is back to a smaller scale, 1,000 feet across, left to right for this feature. Here's the hole or trough, and here's the hill. I've circled the whole thing in orange. Here is a ridge of basalt rubble that I think is also perhaps glaciotectonic, shoved from off to the left into a moraine-like pile, or a ridge anyway. And then a tongue of the ice apparently pushed through this ridge and excavated this trough and shoved the basalt down to here to make this hill. This type of feature that has a trough that's down and then it goes up to a hill at the end, there's a name that was made up for this type of feature based on seeing glaciotectonic features like this up in Canada from the Laurentide ice sheet. It's called a merdlin. Down here in the bottom right is that word. That's the word drumlin rearranged, because instead of going up and down like a drumlin, these features, they start out down, going down glacier direction. They start out going down into a trough, and then they come up into a hill. So an inverted drumlin, even though they have a somewhat different origin than a drumlin from glaciotectonics, rather than just erosion and redeposition. But anyway, they're not the same as a drumlin. The word merdlin is a clever, maybe you think it's clever, play on the word drumlin. One more slide before we wrap up. What is the extent of this glaciotectonics on the Waterville Plateau? The Waterville Plateau overlaps with Moses Coulee, one of the major channels of the Channeled Scablands. And there's a remaining question in the research: how did water get into Moses Coulee? Because it's hard to find channels down low enough to get the water out of the Columbia River system off to the northeast and out of the maybe out of the Grand Coulee area to the east. Anyway, how did the water get into Moses Coulee, especially if it came from glacial Lake Missoula, where we don't see a complete set of obvious channels into Moses Coulee, and that's still being researched. And that goes back to that question: did water get into Moses Coulee from under the ice sheet, from under the Okanogan Lobe? Maybe a somewhat reduced version of the underburst hypothesis. That's still open for argument and research in the geological community. But what about the glaciotectonics? So here, if you can figure out this picture, I put a scale on it. So again, it's like 4 or 5 miles wide, northeast to the top. The town of Withrow, which is just beyond where it was glaciated, is off to the bottom left, a mile or two, slightly out of this topographic map. And it's a little bit hard to see the shapes of the Earth's surface on this topographic map. But nonetheless, here's mostly marked in green by coincidence is the Withrow moraine, these hummocky hills, irregular hills and troughs in between, and a few valleys that were eroded by post-glacial, beyond the glacial meltwater as well, cutting through some of the Withrow moraine. But behind the Withrow moraine to the north and northeast, if you go up far enough, you reach this escarpment or scarp, a small, relatively low cliff eroded into the edge of the basalt here. Okay. So what eroded the basalt away to make this escarpment? It does not look like normal stream valley shapes. I think it may be that the ice flowing across here was in many cases on a glaciotectonic scale, taking out large chunks of the basalt and transporting it down the ice flow direction towards the south-southwest. So a lot of this material could have been eroded by the ice itself in glaciotectonic form, large slabs, and transported down here and partly cracked apart, broken apart into more rubbly material on the way and piled up into the Withrow moraine. Okay. There are some high elongate features between the scarp and the Withrow moraine that look to me like glaciotectonic pileups on top of the intact basalt flows, which is making up the rest of the Earth underneath. So I think it may be that glaciotectonics was quite extensive, certainly far more than previously realized, on the Waterville Plateau. In this image, Withrow Moraine is down here, going north-northeast up the ice flow direction. You come to this scarp or low cliff where the edges of the Columbia River basalt flows here have been eroded away. I think that may have been largely due to glaciotectonic sized slabs being taken out of the retreating scarp and moved this way by the ice, and much of it piled up to form the Withrow Moraine. In between the scarp and the Withrow Moraine are elongate streamlined bed forms. Some of them are high, hilly, rubbly basalt piles that may be glaciotectonic hills that were left in transit without being taken all the way down to the Withrow Moraine at the end of the glaciation. So if that's the case, we have several square miles here of glaciotectonic features, including the Withrow Moraine itself, largely a glaciotectonic pileup of a style that may be unique to how the Columbia River basalt reacts when it's subjected to glaciotectonic stress. It doesn't fold and bend like layers of glacial drift or sedimentary rock do, or how granite would either, the very different jointing style in the Columbia River basalts. So that's a suggestion that we need to look at just how extensive glaciotectonics was on the Waterville Plateau, and that to begin with, it was certainly more extensive than previously realized, including those named hill piles I listed on the earlier slide, most of which have not previously been identified as hill-hole pairs from glaciotectonics. Okay, so let's get to the conclusions. The Okanogan Lobe landscape is worth studying. I think that's clear for all the reasons I listed, and then I have my own personal motivations that weren't written down there that I talked about. But the general motivations are strong, and there's still ongoing research on the Okanogan Lobe, on the Cordilleran Ice Sheet, and on the Waterville Plateau into the terminal moraine portion of the Okanogan Lobe for good reason. The underburst hypothesis, according to my analysis and my read of it, it fails to hold up to the tests of logic, physics, and the evidence in the landscape that the Okanogan Lobe and the connected channeled scablands along the south of the Okanogan Lobe are very conveniently there to provide for testing that hypothesis. Okay, so the hypothesis fails in that regard. Tunnel valleys, no, back up. Drumlins and other elongate streamlined bed forms were formed primarily by erosion by ice, by glacial erosion, and to some extent by redeposition of eroded sediment in the downflow direction by the ice. And this was under a warm base glacier where this extensive erosion and to some extent transport of sediment went on under the ice sheet with water present, but not mega flood scale for forming things such as the drumlins, not at all. Tunnel valleys, the valleys in this study area are a complex mixture of actually several types of valleys, some of which may be true tunnel valleys in the genetic sense that they form by subglacial channel ice flow, but those are hard to pick out and recognize and verify because many of the valleys, as I've talked about, show definite evidence of glacial erosion by moving glacial ice, and many of them were meltwater streams off to the side of the retreating glacier during the end stage, during glacial retreat or down wasting and stagnation of the ice sheet from the landscape. And there's also reverse drainages and captured streams, including on bigger rivers such as the Similkameen River, that add to the complexity of these things we call tunnel valleys. At any rate, none of them require or point to giant subglacial floods on the scale of the meltwater underburst hypothesis, going back to Shaw and others 1999, in how they originated. The Great Terrace is the largest came terrace deposited alongside the remaining part of the ice sheet that was along the bottom of the Okanogan and Columbia River valleys at the end of glaciation. And it's the last stage of, or the going out with a bang stage of a succession of terraces that came down from higher elevation as the ice sheet was wasting away and thinning and stopping at various levels
along the side of the landscape on its way down to the last remnant in the bottom of the main valleys. And that's consistent with those outside the glacier meltwater streams that cut through the landscape to, to, to let the water escape where it was dammed off by the retreating glacier in the side valleys. So those two work together for an aggregate of evidence that makes good sense according to that theory, or at least that hypothesis. Okay, extensive tracts of the Waterville Plateau are glaciotectonic, and that needs to be taken into account in studies of the geomorphology of the Waterville Plateau and how it may connect to such things as the origin of Moses Coulee and the Channeled Scablands. And that's it. This is Ralph Dawes of Wenatchee Valley College, thanking you for listening to this talk about reading the Okanogan Lobe glaciated landscape or glacial landscape. There's my email address if you want to get in touch. And I wish you well. And if you get a chance, take another look around or go there if you haven't been there before to this glaciated landscape in the Okanogan country. It's beautiful, it's different, and it's also got some puzzles left that need to be figured out. So take a look if you get a chance. Thank you.